So in this video, I want to talk about the induced current in a wire loop. Alright, so you can have induced current if you have a change in flux. Alright, so we'll go ahead and want to talk about flux first. So magnetic flux is magnetic field times the area of a loop times the cosine of certain angle. Alright, so let's see. If you've got yourself a loop, I'm gonna draw a square loop. So we're gonna kinda look at this loop. I'm gonna try to draw it 3D, sort of looking at it sideways here. Okay, and there's where it goes off to the battery or whatever. So here's our loop, and if we define a so-called area vector pointing straight out of it, that's how we're going to talk about phi. So let me grab another color for magnetic field. So we'll have a red magnetic field coming through at some funny angle like that. And so phi, this is the angle that the magnetic field makes with the area vector. So that's phi right there, or you could write it right there. Okay, so there it is. So magnetic flux it's kind of an abstract concept, but it's something about magnetic field times the area that the field is going through, right? So here's the equation right here. Okay, so back to current. In order to have an induced current, you have to have a change in magnetic flux, which means that you must have either a change in magnetic field, or a change in area, or a change in angle. Right? Look at the equation. If flux changed, one of those three things must change. Alright, so let's imagine a changing magnetic field first, and see how that affects the direction of induced current. So, let's see. I've got a little room right here. So let's look at a loop. This time we're just going to look straight down at this loop of wire. And let's say we know the area of this loop. You know, the area is not changing. And there's some magnetic field. Oh, let's say the magnetic field is going into the loop, into the page here. Okay. So if we have this situation with a into the screen facing magnetic field, let's find out the direction of the current if the magnetic field is increasing. Okay? Alright, so the way that I remember this, or the way that I figure out how to do this, is that these loops are basically very contrarian things. They want to prevent any change in their flux. So if we increase magnetic field, we're increasing flux, right? The loop is going to want to try to counteract that. So let me show you what I mean. The magnetic field is increasing. I'm going to denote that by drawing some extra x's, right? So this is like the magnetic field getting stronger. So there'll be some more everywhere. But all of a sudden, from the loop's perspective, there are more x's. The flux has increased. The number of x's has increased. The loop does not like that. So it's actually capable of creating a magnetic field. The loop is going to create a magnetic field pointing in the opposite direction in order to cancel out this change in flux. So x's are into the page, dots are out of the page. So the loop is going to create within itself this magnetic field, induced magnetic field, pointing in the opposite direction, because that will cancel out these new field lines that were added due to our increasing magnetic field. So now that we know the direction of the induced magnetic field, we can use the right-hand rule to figure out the direction of the induced current. Okay, so it's hard for me to show you the right-hand rule, but you can figure it out. If the induced magnetic field is pointing out of the loop, then the direction of the induced current is that. So that's our induced current. Okay, so I'm going to do a few more of these because you just need to keep seeing them, really. So we'll just scroll down a bit. So now let's say, take a similar situation. We've got a we'll just do the same direction for the magnetic field. and this time we'll say it's decreasing. Okay, you can probably guess what the answer is going to be, but let's go through the steps. So if the magnetic field is decreasing, then all of a sudden we've got less and less x's, right? In fact, okay, so this is where we're starting. And the magnetic field is decreasing, so we're going to lose some of these guys, right? As the field gets weaker, we're going to get fewer and fewer x's. That's one way to think about it anyways. But loops do not like change in flux, right? Losing some of those magnetic field lines means that the flux in that direction decreased, so the loop is going to create a magnetic field to put those back in. Okay? So before, when the change was an increased magnetic field, the loop had to cancel that out by putting a magnetic field in the opposite direction. But here, in this problem, our magnetic field decreased, which means the loop has to create a magnetic field in the same direction to prevent that change, to keep the same total flux. And so now that we know the direction of the induced magnetic field, right, we can figure out the direction of the right hand of the induced current using the right hand rule. There it is. Okay, so you could do the same problem a couple different ways using magnetic fields that are coming out of the page instead of going into the page, so you might want to try that. But I'm going to go ahead and talk about now the idea of changing the area of the loop. Okay, so we just talked about the change in field. So let's see. So if we have a loop, let's do it right over here. And it's got some area here, yeah, fine. And it's got some magnetic field in it. Say we'll go with dots, I guess, doesn't really matter. And the area of this loop is decreasing. Okay, so let's see about that. I want a few more dots, actually. Alright, so the area of this loop is going to decrease. Well, let me use my computery tools here to denote that. Alright, so let's see if I can do this. Not bad. So the area of the loop is decreasing. So this could happen because someone, pulled some of the wire away and stretched it smaller, right? So the field didn't change in this problem, but the area of the loop decreased. However, the effect is similar. See what happened? Now the loop has fewer dots, right? It has less magnetic field lines coming out of the screen. So, well, what's it going to do? It's going to cancel that change out by adding magnetic field lines. So let's see what color I'm using. This color. So it lost. Let's just use my example here. So we had 1, 2. So we have 3 dots in the loop. We lost 1, 2, 3, 4, 5, 6, 7, 8. We had 8, so we lost 5. So it's going to put. I mean, this isn't really important to get the number right, but I'm just making sure you have the idea. It's the same sort of thing. We lost. The area got smaller, but if you look at the picture like this, it's like we just lost magnetic field again. We lost magnetic field lines. So it tries to put those back in, and there we have it. We figured out the direction of the induced magnetic field, so we can find the direction of the induced current. Let's see, so it's coming out, so like that. All right, so this is all the same problem, right? Okay, and this problem could be redone with the loop getting bigger, right? Or the magnetic field pointing the other way, probably like 4 different combinations. So go ahead and try some of those if you like. In the meantime, I'll talk about the last change possibility to get a change in flux, which is the change in that angle there. Okay, so this one might be a little hard to draw, but we're going to go ahead and look at a loop from overhead, just like we've been doing. So looking straight down at this loop, and it's got some kind of magnetic field in it. Big surprise. So these magnetic fields, these red ones I'm drawing, by the way, have all been from some sort of external source. right? They're not being caused by this loop. It's from some like magnet or some machine that you can't see. But the induced magnetic fields that I've been drawing in light green, those are caused by the loop. Alright, so here is our loop. In this picture, it looks like the angle is 0, right? Think about that. Look at this picture. The magnetic field line, the angle is with respect to the area vector, right? And so the magnetic field lines are coming straight out at me, and so is the area vector, right? If I was to draw the area vector in, it would look like that, right? If you can imagine that. So they're both coming straight out, so the angle in this picture is 0. Okay, so now let's say that this thing gets rotated. So let's rotate the loop about this axis. Alright, and so from our perspective, it's just going to, let me do the old copy and paste here. And I don't know what angle we're going to rotate it to, but we're going to rotate it missed it. And really all that would look like is this. Alright, can you imagine that? It's really what's happening is it's rotating, but from our perspective it kind of just looks like it's being squished down like that. And, well, the effect is exactly the same as changing the area. Right? When the area got smaller, we had less field lines. Same thing here. It's like if you imagine just taking a butterfly net or something and trying to catch a bunch of falling, rain? I don't know why you're catching rain in a butterfly net. But if you start rotating the net, you're not going to catch as many raindrops. Sorry. I know it's important. So we've got fewer magnetic field lines going through there. That means that the flux in that direction is decreasing, right? So this loop is going to replace those dots that it lost. You know, it lost, I don't know how many, I probably put too many in, but it lost some of these dots, and it's going to put them back in. And now that we have the direction of the induced magnetic field, just jot that down. Okay, so that's the induced magnetic field. Now that we have that direction, we can figure out the direction of the induced current, which would be this way. All right. So yeah, most of my examples ended up having the induced magnetic field be in the same direction as the original magnetic field. However, that is not always the case. Look at our very first example. The induced magnetic field in light green is in the opposite direction of the increasing magnetic field. In that one, I put the increasing magnetic field in orange. And so the induced magnetic field, it just has to cancel out the change in flux. Okay, all the loop can do is create a magnetic field. So it creates whatever field it can to cancel the change in flux. Here we had an increasing magnetic field, so we have an induced field in the opposite direction to cancel it out. Here we have a decreasing magnetic field, so we have an induced field in the same direction to cancel the change. Here we have a decrease in area, which is causing us to grab fewer and fewer field lines. So we have a induced magnetic field in the same direction because it wants to put back in those field lines that it lost. And pretty much the same thing here. Now, maybe I should have put the field in a different direction in one of these, but oh well. So check these out. Try and make yourself a couple other examples that I didn't come up with, and see if you can do it. Thanks.